Hi everyone, I'm Pornapat and I am Hassalak. We are the representative from Professor Richard physics class at Ekamai International School. So we are invited by the Baijak crew to be part of their team and we will be observing their project of orbiting the Earth.
Hi, we are the Baijak crew.
My name is Sitatham and I'm the engineer of this Baijak crew and I'm the one to design this rocket Baijak 101.
Hi, my name is Ramil. I'm the scientist in charge of calculating and researching the information for this trip.
Hi, my name is Thitirat and I am the commander and pilot of this project.
Okay guys, so this is our NASA in the Kerbal space branch. And here, let's go into the vertical assembly building to build our rocket. Okay, so this one is the model Apollo 100. The previous one, can Mr. Ramil explain?
Okay, so this is just like a mock-up model for the Baijak 101. So, but we didn't use this one because it failed last time. So we are going to create a new one, and Sitatham will show you how to do it.
Okay, so first let's start with the command part. This one is the function for the command module in which we all five will stay in here and watch and observe things in space. And next, we will add the parachute. The parachute will let us land safely. Next, we will add this thing. It is called the decoupler. This decoupler is the one to add a stage. As you can see, it will add another stage so that when we land, we will only have the parachute and the module of the command module like alone without the gas. Next, let's add the engine.
Wow, there are so many of it. How do you know what to choose?
Oh, it's very simple. We just need to consider two factors: the mass and the size of the spaceship or the rocket, and another one is the type. There are three main types. The fuel tanks here, it contains fuel and oxidizer. Do you guys know what is oxidizer?
Yes. Oxidizer is a type of chemical which a fuel requires to burn.
Wow, you're very smart. Mr. Richard is very smart too. Okay, next type of the fuel or engine is this one. It is the liquid fuel engine which provides the thrust for this one for the fuel tank. And this special one, the last one, is the solid fuel booster, in which it can work on its own, providing thrust and fuel. For this stage, let us put this FLT 100-200 fuel tanks, two of them. Okay, and for the next step, we will put this thing together with the fuel tank, the LV909. And for this is our upper part. To finish the upper part, we will put this decoupler again so that it will be completed. So after we finish the upper part, which is the one to let us orbit the Earth and let us maneuver up there, we will start with the lower part, the part we will need to launch the rocket. So let's start with fuel tanks, FLT 400, which contains 180 liquid fuel and oxidizer of 200. I think. Next, let's pair it up with the liquid fuel engine. The last one we used for the upper part was LV909, which although contained lower thrust, but it has higher efficiency. So let us use LV-T45.
Why LV45 if LV30 have more thrust?
Oh, it is because although LV-T30 provide more thrust, but for LV-T45, the nozzle, or it is this part can be moved, and so that we can steer and change the direction when we launch the rocket. Okay, next we will start with the wings, the aerodynamic parts. Can Mr. Ramil please explain?
Okay, so we need to put the wings because in order for us to have the stability, we need to put the wings, and wings also benefit us in controlling the direction, maintain its orientation so that it won't collapse while it's in the air, and also serve to locate the center of pressure and the center of gravity so that it will be more stable.
Wow, such knowledge, yeah. Okay, so clap hands. Guys, don't be so stressed, we are shoo. Okay, next, let's add some additional fuel so that we can launch into space successfully. Let's use the last type of solid fuel booster. So for this one, it will provide thrust in spacecraft launches from launch pad. It is used for like almost every NASA space or rocket ship.
Oh, so you mean this one is better than the liquid engine?
Also, they have disadvantages and advantages. For this one, it provides greater thrust, and it also reduces the launch vehicle mass because it reduces the amount of liquid fuel used. But for the liquid fuel we use up and this one, it is better because we can control the amount of heat and the amount of fuel and rate of burn when we are at flight.
Sitatham, I think you forgot something.
Oh yes, the structure. This one we need to put the radial decoupler because
We need to eject it after using it, right?
yes, when the fuel of this solid fuel booster run out, so we can eject it out and we won't need to carry large mass up in the orbit. Okay, for the last part we will add this structure. It is called modular girder segment, which is a very special segment used to spread the force of the engine because it has so large force that it might break. So we will add another decoupler first so that we can eject before we launch. Here, so this is the completed rocket. And now we will need to reduce the amount of thrust. Also, Ramil, why do we need to decrease the thrust to like 66 to 2/3 of the solid fuel booster?
Yeah, so that the rocket could get longer burn time and spend less time fighting against the wind.
Ah.
Which is the wind is the aerodynamic drag.
What is aerodynamic drag?
Oh, you don't know? Sir Richard just told us. It acts against the thrust of the rocket.
Yeah, so it will act this way while the thrust will push the rocket up. The aerodynamic drag will push the rocket down. Okay, so now we're ready for the launch. It's time for our pilot to launch. Let's go to the launch pad. Yeah!
Okay, so now we're going to fast forward the time so you can see the orbit of the Earth. Okay, so now as you can see, the stars are orbiting from east to west, and that is the reason why we need to turn to the right 45 degrees when we're in flight. Okay, so now we're going to adjust on the staging.
Yeah, so we adjust this in order to make sure that the modular girder segment and the gas or the solid booster will be ejected at the same time.
Okay, so you would probably think that we should adjust the throttle to its full level, but actually we can just launch it by getting it to the 30%. I'm just gonna press shift. Okay, and now I'm going to enable the SAS system.
So what is SAS system?
So SAS is derived from the word Stability Assist System, which will help in stabilizing the rocket.
Okay, so now we're going to launch a rocket now.
Yay! Wow! Oh my god!
Oh, so we need to launch the rocket vertically first, so there will be no drag from the atmosphere, right?
Yeah, that's right.
Oh, so why the rocket accelerates? Gravity will bend the trajectory downward.
Yeah.
So now all we have to do is wait for the fuel to run out.
Yes, and then we will eject it like as we attach the decoupler just now in the laboratory of the vehicle assembly building.
Okay, so now the fuel has run out, so I'm going to press full throttle and eject.
Wow!
Space again to enable it, and switching the surface to orbit. So now we've reached 10,000 meters and we can press D to start, turning to 45 degrees.
Oh, it's crazy.
And when we've done this, we can go to the map and see space.
Wow!
This blue line indicates about the trajectory line of the rocket. So we all we have to do is wait for the rocket to reach 100,000 meters so that we will have a great distance away from Earth.
Wow! So now you can just chill, guys. Do you want some snacks?
So, Miss Sitatham, could you please tell us about your job, like more about yourself? Oh yeah, sure. Excuse me. Actually, I've been here for like 20 here like since I was in high school. And I have made many spaceships here. This one is the model of my Saturn U that went to Saturn. Like I made it 4 years ago, and wow, this one Apollo CSM, the famous one. Yeah, I made it.
Like 5 years ago, and
So now we reach 100,000. So we're go-
sorry.
so we're going to press X to stop the throttle. And now we're going to create a maneuver. The maneuver will create an ideal orbit around the Earth. So this is my ideal orbit around the Earth. It doesn't have to be exact once I've tried to make it reach. As long as it orbits Earth, it's okay. So now, as you can see, the burn time is 49 seconds. And my node-in time is minus 2 minutes and 5 seconds. So right now I could just wait for the time to reach about 50 seconds, and then I'll just press space to make it throttle again.
So the orbital is ellipse because of Kepler's first law, right, Ramil? Or which law is it? I can't really remember.
Sitatham, you're out of frame.
It's the first.
You are out of frame too. Yeah, it is the Kepler first law.
Okay, so now it has reached about 54 seconds for the right time. So I'm just gonna tilt this rocket more. And I'm going to go full throttle again.
In space, if you are moving, you will keep moving in a straight line forever. This comes from one of Newton's law of motion, that an object in motion stay in motion and an object at rest stay at rest unless acted upon by a force.
And that law is the Newton's first law, right?
Yes.
Okay, so now the fuel is run out. I'm going to eject, and
Okay, so we just ejected the lower part that we used for launching, and now we left with the upper part for orbiting and for maneuvering up in space.
so now we have to let these meters per second run out and the burn time into its full. As you can see on the map, the blue line starts to cover the Earth, and as we go on, as the time increases, the blue line will eventually circle the Earth and it will be an orbit.
So from what I know, eccentricity is a number to describe the shape of the orbit. But the closer the eccentricity is to zero, it will be more circular. And if it's greater than 1, it will be parabolic or hyperbolic.
Okay, so now we're in total orbit because as you can see the screen has also tilted. Now let's check on the map. As you can see, it's not really that perfect with the yellow line, but the blue line has encircled the Earth and we're now in full orbit.
Yay!
Wow.
Yeah, so if you're in a circular orbit, your speed will not change, therefore the planet is pulling you straight down. But you're already moving fast enough away from the planet, which is Earth, that you move in a circle. So you're actually in a free fall. But you are moving so fast that you miss the planet every time. So in a stable orbit, your velocity depends only on your position in that orbit.
As you can see, even without throttling anything, I am already in orbit in space. Okay, so we can actually check that by fast-forwarding the time. So now we're circling the Earth.
Wow! Mission accomplished!
And this is the other side of the Earth, which it doesn't face the sun. Even on the map,
From the other side.
we can check that. So this triangle thing is a rocket, and it's now circling the Earth. Okay, we'll just go one more circle before landing.
So our next mission is to land on Earth, and that is our final mission.
Okay, so now we're ready for a landing. So in the first step in landing, we need to reverse the head of the rocket to the opposite direction. Okay. And our point will be exactly at the yellow circle. Okay, so now we're ready to decrease the altitude by throttling it only a little bit. So let's shift. As you can see, the altitude is already decreasing. And we have a large amount of fuel left.
Okay, so the physics of landing and launching is exactly the same.
Yes. When we
Oh my god! Oh my god!
When we launch, we need to escape velocity of the gravitational force of 9.81 meter over second squared. And when we land, we will fall with gravitational force, but with air resistance as the opposite force.
I learned from Professor Richard that when an object moves toward a source of energy, we call it gaining kinetic energy. But when it moves away from the source of gravity, we call it gaining potential energy.
So we can fasten up the process by throttling more.
So when we land, do we still need fuel, Mr. Ramil?
Yes, of course, fuel is the most precious thing in landing because we need to being in control of the altitude and also the velocity.
Wow! Okay, so now we eject to left only the pod and the parachute.
We can set the orbit back to surface.
Oh my god.
Okay, so now we're facing Earth.
Are we going to be safe? Are we landing safe?
Yes, of
Yeah.
course, this is my Baijak 101, guys. This is very safe.
Yeah, and of course, because this is my calculation, it won't be any errors.
Oh, I feel so safe now.
Because I was once in Mr. Richard's class too.
Yeah, we are
That
all
made me so
over.
confident.
I trust you guys by Jack crew.
Thank you. We
are
Wow, what is happening here? Oh, calm down,
Calm
guys.
down.
It's
Okay,
just
so
kidding.
before releasing the parachute, we need to let the heat goes out first.
It's okay, guys. This
We will stay
this type of the pod is very high heat resistant, so it will be safe. We will be safe.
Oh my god.
Wow! Here's the parachute.
Gotta go swimming next. Oh my god.
I'm excited.
Although we're landing on water, but we'll be safe because of our parachute.
Yes, and this pod is designed for
Yeah, did you hear the
safety
boat
water
sound?
landing.
It
Oh
passed by
yeah, the
just now.
boat sound.
Okay, so now we just wait for the altitude to decrease and we'll be landing safely.
That's caught fish.
Come on, camera, guys.
By the way, where are we? Are we in Africa?
I think this is the Pacific Ocean. Let me check the
Yeah.
GPS. Oh yeah, Pacific Ocean.
Oh my god!
Safe?
We landed!
She will be happy.
We have successfully landed on Earth. When energy is greater than zero, the vehicle is on an escape trajectory. And our mission in Kerbal Space Program is taught about the concept physics of friction, acceleration, gravity, and velocity. Bye guys!